Good day, ladies and gentlemen. My name is Alexey Doronin, and I would like to tell you about ray tracing and how to apply it for light field display. Also, my presentation covers the application of ray tracing for HoloVisio light field display, which is manufactured by Holographica company. This methodology and conclusions can be applied for most of current light field displays as well. The main point of my presentations are the following. First, ray tracing is better than rasterization algorithms. Second, it is possible not only to construct beautiful images with the help of ray tracing, but also very precise ones. When we compare with conventional rasterization algorithm. And third, this allows us to apply any post-processing algorithms in correct way. By post-processing algorithms, we can mean tone mapping, screen space ambient occlusion, or any other algorithms that would require us additional textures like depth map or positions map and so on. The only difference in application of ray tracing to HoloVisio light field display when compared to application of ray tracing to conventional display is the generation of primary rays. Everything else, including generation of acceleration structure, handling of acceleration structure traversals, is the same for light field case and for conventional monitor case. First, let me remind you what is ray tracing. Ray tracing is a method of visualization virtual 3D scenes. In conventional case, primary rays are emitted from the camera. It can be perspective or orthographic camera, and each primary ray goes through the pixel of the screen. After this, primary rays are checked on intersection with virtual scene environment. At the point of intersection, secondary and shadow rays are generated. Shadow rays are spawned towards each light source, and secondary rays can be considered as the continuation of primary rays in case if material has refractive or reflective property. And now I would like to tell you what is HoloVisio light field display. HoloVisio light field display is the horizontally parallax light field display. It consists of diffuser surface and row of optical modules behind it. Each optical module behaves almost like ordinary projector. It takes 2D texture as the input and projects it towards the diffuser surface of the screen. The diffuser scatters all incoming rays of lights into different directions, but in horizontal directions it scatters much less than in vertical. The human observer can perceive the final image standing in front of the diffuser. What observer sees at a particular position in space is the overlapping vertical stripes of different optical modules. The user can move in different horizontal directions. In this case, the user will see different places of optical textures. Keeping this in mind, we can simulate the parallax effect of a given virtual scene. The only thing that we should do is to submit the proper 2D texture to each optical module. Let me illustrate it with an example. On the left side you can see the virtual 3D scene rendered with the help of a perspective camera module, which is conventional case for all current 2D monitors. This virtual scene consists of a module of statue inside the cubic environment map. As you may notice, both statue and environment map are very detailed and sharp. On the right side you can see the 2D image that human observer would perceive standing in front of the HoloVisio light field display. This image is generated with the special utility that simulates the work of diffuser. In contrast to previous image, the current image doesn't look sharp and detailed. But this type of blur cannot be achieved by some Gaussian or box filter. In fact, this blur is different in all positions of the image, and in horizontal direction it is stronger than in vertical. However, in case of HoloVisio system, the user can move from left to right side and perceive the scene from different perspectives, as you can see now. Please keep in mind that this parallax effect is achieved on the single set of optical module images. The only thing that is changed is the position of the user. And now I would like to show you an example of optical module image. As you can see, for this specific type of holovisio geometry, the optical module image is composed of 3 parts. Each part uses its own specific type of projection. The central part has a shape of slightly skewed rectangle. 2 side parts have pyramidal shape. Although the size of central part and side parts are very different, they all cover approximately the same range of space. The details of the statue are rendered in very sharp manner, because they all are very close to observer. But the details of environment map are blurred in horizontal direction. This is because the environment map is far from the observer. You can see it very clearly on the central part of image. The whole image that you can see now is the evidence that we need to use very specific type of projection for the construction of optical module image. And this type of projection is very different from perspective camera model. This is why the conventional methods of working with perspective camera model are not applicable to our case. Therefore, it is best to use ray tracing based methods. Now let's talk about how to apply ray tracing for holovisio case. Let us consider the simplest configuration of holovisio light field display. This configuration can be parameterized in the following way. We represent diffuser as a 2D plane. In current parameterization, possible positions of the user are represented as an observer line. This line is located in front of the diffuser. Please keep in mind that in reality, user can take any position in front of diffuser. But we assume that the observer line is a line because this parameterization gives us enough information to construct the light field with horizontal parallax effect. The positions of the optical modules are also represented as a line. The line of optical modules is placed behind the diffuser. With this parameterization, it is very easy to see the difference between holovisio case and conventional 2D case. In 2D case, we would generate an image for the camera that is placed on the observer line. But in holovisio case, we need to generate the images for each optical module separately, and optical modules are placed behind the diffuser. And now let us consider how the optical module works in conjunction with the diffuser. Each optical module emits the rays of light with color information, in a similar way as ordinary projector does. Each ray from the optical module hits the diffuser at some position. From this point, the ray of light is diffused with the help of diffuser. And since we are interested only in those positions of the user that are placed on the observer line, we can assume that the ray of light goes through the position of the diffuser towards the appropriate position on the observer line. In order to apply ray tracing, we need to generate the set of primary rays for each optical module separately. The corresponding primary rays will start from the observer line and go towards the diffuser. They will repeat the path of optical module rays, but in inverse direction. Generally speaking, none of the primary rays should share the same origin or direction. Therefore, we need to store the origins and direction in separate textures. The following example explicitly illustrates why ray tracing is better in our case than conventional rasterization techniques. We have rendered the virtual scene that consists of a single triangle. The corners of this triangle are rendered in RGB colors. The color values vary from 0 to 1 per each channel. The RGB value equals to the world coordinates of the corresponding point. For example, completely red point has world coordinates of 1, 0, 0. There are 3 images on this slide. Each of them is the part of optical module image. Left image is rendered with the help of conventional OpenGL graphics pipeline, using linear interpolation to get the intermediate positions between the corners. Right image is rendered with the help of ray tracing. This image shows the correct projection from the world space to the space of optical module. As you can see, the surface of triangle is not linear anymore in space of optical module. The intermediate image shows the difference between left and right images. Most difference is located on the sides of triangle, but there is also a difference inside the triangle itself. The intermediate image is obtained with the help of Compressionator tool. And this, ladies and gentlemen, concludes my presentation. Thank you all for attention. I would like to express special thanks to organizers for the opportunity to prepare this video, and to reviewers for nice and fruitful feedback. I need to say that this research is a part of European Union Horizon 2020 program, specifically of two networks, ETN-FPI and QONet. I'm very sorry for not being able to attend this conference, but if you have any question, please feel free to ask. You can write me a mail about any specific detail that you are interested in, or alternatively, you can ask my colleagues who are present on this conference. Aaron Cherkassky can reply to anything related to HoloVisio live field display. And Peter Kara is the third author of this paper and a member of QONet. Thank you all for attention once again, and have a nice day.